Welcome to the course on VLSI physical design with timing analysis. In this lecture, we will discuss about the static timing analysis for combinational circuits. So, in this lecture, it will include the how we can find a critical path of any circuit with an example. So, in the last class we discussed about the arrival time and the required time. So, in the today's class we will discuss this one in detail with an example. So, if I write down the formulas for the inverting types of gates, okay. If I write down the formulas for the inverting types of gate. So, if I have any kind of inverting type gate, so I have two things, one is input arrival time and output arrival time. So, what is the first one I need to calculate is the output arrival time or output rise arrival time is basically max of input fall arrival time plus rise delay. Okay. Similarly, I have output fall arrival time is basically max of input rise arrival time plus fall delay. Then this is for the output arrival time, this first and the second is the output arrival time. Then if I know the output arrival time, then how I can find the input arrival time. So, in this case I have to find out the input rise arrival time. Okay. So, since I am finding the slag, so here I also can write this as input rise required time. Okay. So, input rise required time is basically minimum of output fall required time minus fall delay. Then the fourth one, input fall arrival time, or I can write input fall required time, because the required time is needed for my slack calculation. So, I need to do minimum of output rise arrival time minus rise delay. Okay. So, these are the four formula I will use throughout my calculations. So, we will take an example and discuss how this is happening. So, the example 1 here. So, I have NAND gate followed by a NOR gate, then a inverter. So, 3 gates. Okay. It is easy to explain. So, I took a very small example. So, the these are the rise and fall delay, these are the rise and fall delay, these are the rise and fall delay. So, this is my node A, node B, this is node D, this is node E, this is node F. So, each of the nodes I need to find the first arrival time, and this is the nodes basically input C, which is going to input of the basically my NOR gate. So, I will what is my task here, or what is the question here? If this gate if this netlist or the circuit is given to me, and what are the things given to me here? The given is the rise delay by fall delay for each gate, it is given to me. Then second thing what is given to me, my input node arrival time is given. So, what are the primary inputs here? A, B, C. So, the arrival time, okay, both rise and fall, let us say the basically the rise and fall arrival time of node A, rise fall arrival time for the node A is basically 0 0 0 by 0. Similarly, the rise and fall arrival time for node B is also 0 0, and arrival time for the node C is also 0 0, that is given to me. And one more thing is given to me. What is that? That is called the required time. The required time at node F is 5 by 11. Okay. So, these are the things given to me. What I need to find it out? I need to find it out basically the arrival time, required arrival time at each node. Okay. I need to find the required time at each node, and find the, this is the first, then find the slack at each node. Then the third point is find the critical path in the circuit, correct. So, this is the thing. So, now I will basically solve some part here and some part in the second slide. Okay. So, here if I take for the node A, I will start with the node A. Okay. So, node A, I have the arrival time is given to me. So, whenever I am writing arrival time, the basically it is not a division, it is basically top one is saying the rise arrival time, and the bottom one is telling the fall arrival time. So, this is your rise arrival time, which is given in the, this is the fall arrival time. So, this is given. Now, now I cannot find the required time right now, or slack I cannot find. So, I will send give some space there. So, for the node B, okay, node B, I have basically arrival time, same arrival time. So, this is 0 by 0. Node C also the same thing. So, I will take to the next slide. Now, I have the same circuit. Okay. So, now I have to do it for the node C here. Okay. Node C arrival time, rise and fall is 0 by 0. Then the node D arrival time is basically, if I take the node D arrival time, so it will be basically 2 by 3. Why it is 2 by 3? I will write the reason for here, for the reason here. Basically, the input arrival time, fall arrival time is 0, input rise arrival time is 0, then the rise delay is 2, and the fall delay is 3. So, these two will be added up to give me this one, these two will be added up to give me this one. So, now I have this node basically node D, then node E. Okay. I have node E arrival time I need to find it out. Okay. So, the node E arrival time is basically, I need to find it out. So, I will write the reason here. So, the input arrival time, input fall arrival time equals to node E. The input fall arrival time is 3 and input rise arrival time is basically 2, and you have the rise delay equals to 4 and the fall delay equals to 3. This corresponds to basically corresponds to this gate, okay, NOR gate. Now, this arrival time will be 3 plus 4 and 2 plus 3. So, 3 plus 4 is 7 by 5. So, this comes from here, this comes from here. Now, I will do the next node. Okay. So, I have one more node is there, node F. I have one more node is there, node F. So, node F, I have arrival time. So, the arrival time here is the, I have to do two things, input arrival time fall which is 5, input arrival time rise equals to 7, then I have a rise delay of the inverter, rise delay of inverter is 1, then the fall delay of inverter is basically 2. So, here if I do these additions, the arrival time at the node F is 5 plus 1, then 7 plus 2, this is basically 6 by 9. Okay. So, this is my arrival time. Now, I have given the required time. So, required time is basically 5 by 11. Okay. Then my slag here is basically required time minus arrival time. Okay. So, I need to subtract my rise required time, okay, rise required time with the rise arrival time. So, required time rise will be subtracted from arrival time rise. Similarly, rise required time fall will be subtracted from arrival time fall. So, it will be, if I do the subtraction, this will be 5 minus 6 divided by 11 minus 9, it is basically minus 1 by 2. So, now I have to go back. So, if I have to go back here. So, now I need to find the required arrival time at node. So, I have to find the required arrival time here. The required arrival time at this point is basically, I have two things here. One is called my output fall required time, okay, that is 11, output rise required time is basically 5, then fall delay is 2 and the rise delay is 1. So, now the required time in this case will be 11 minus 2 by 5 minus 1. So, it will be basically 9 by 4, okay, 9 by 4. Then the slag in this case, like I discussed in the previous example, slag will be required time minus arrival time at node E. So, this will be basically 9 minus 7 divided by 9 minus 7 for the rise, then it will be 4 minus 5. So, it will be 2 by minus 1. Okay. this is my slack. Slack is basically 2 minus 1, correct. So, now I will go to the node D. Node D, I need to find the required time. So, required time at this point, first I need to find what are the inputs for the required time. I will write down here, then I can do that. So, you have the output for required time. Okay. Output for required time is 4 here. Okay. So, basically the output for required time is the this one, is basically this one, and this will be the for the rise. So, this will be for the rise. So, basically if I can write the output rise required time will be 9. Now, I have a fall delay. The fall delay will be which fall delay? So, now already I have discussed about the inverter, then it comes the NOR gate. So, the fall delay here, the fall delay is the for the basically the NOR gate. Okay. Fall delay is for the NOR gate. So, this NOR gate fall delay will be basically 3, then the rise delay of the NOR gate is basically 4. So, now my required time at node D is basically 4 minus 3, 9 minus 4. So, this will be basically 1 by 1 and 5. So, now the slag I can find it out, the slag at this point I can write down the slag here, the slag final slag I am writing, it will be basically node D will be minus 1 by 2. Okay. So, this is the slag at this point. Similarly, now I have to go for the node C. Okay. So, if I know the required time at node D, if I know the required time at the node D and the required time at this point will be the same, because both the inputs are connected to the same gate. Okay. So, I am writing in the same color. So, this will be copied here. So, this will be 1 by 5. The required time is same, but the slag will be different because your arrival time is different. So, the required time is same, however, the slag at this point will be different. Slag will be your required time 1 minus 0, then 5 minus 0. So, it will be 1 by 5. Now, I will go to the previous slide. So, here I have 2 more points are there. So, for the node B, if I look into the node B, the required time at this point. So, I have 4 things, 4 parameters. One is called my output required time fall, which is 5, then my fall delay. Fall delay is basically the delay of the NAND gate, which is equals to 3. Now, output rise required time is basically 1 here, then the rise delay of NAND gate. So, this is basically your 2. So, we using this one I can find the required time. So, required time will be the first row will give me my rise required time. So, 5 minus 3 by my 1 minus 2. So, this will be 2 minus 1. Okay. Then I can find the slag here. The slag at this point will be 2 by minus 1. Similarly, that required time at this point is same as the required time here. This required time here is same as the required time here. So, the required time at this point will be again 2 by minus 1. Okay. So, now if I have that one, then slack at this point also will be 2 by minus 1. So, here, so now I need to draw the final diagram. So, now I need to find the final circuit with all the slacks. So, I have basically this one. So, here delays are 2 by 3, 4 by 3, 1 by 2, then I have A, B, now I have a okay. So, this is the D, this is C, this is E, this is F. Okay. Now, I need to find write down all the arrival time and slack. So, I am writing for A and B together because both have the same arrival time. Arrival time is 0 and the required time at this point is basically 2 by minus 1 and the slack here is 2 by minus 1. So, this is related to this A and B. Now, for the basically C, arrival time is basically 0 by 0 and the required time at this point is basically 1 by 5 and the slack is basically 1 by 5. This corresponds to node C, correct. Now, for the D, okay. So, the D, what is the arrival time? So, for the D is basically arrival time is basically 2 by 3, okay. Then the required time at this point will be basically 1 by 5 and the slack at this point is basically 2 minus 1 by 2. Okay. So, this is corresponds to node D. So, the node D I put it inside the same circle. Now, basically if I go to node E, I have arrival time. Okay. So, arrival time at this point is basically 7 by 5, 7 by 5 and the required time at this point is basically 9 by 4 and the slack is basically 2 by minus 1. Node E, I put it in the same thing, okay, E. So, now for the F node, okay. So, in this case my for the F node, okay, for the F node the arrival time is basically 6 by 9, required time is basically 5 by 11 and the slack is basically minus 1 by 2. Okay. So, this is my this point. So, the critical path is having the which is having the largest negative slack. Okay. So, my critical path in this design is basically if I write. So, the F rising, E falling, then D rising, then either A or B both falling. So, if I can see here this is negative here. Okay. So, this is negative. So, minus rising. So, this is corresponds to this one, this minus 1 corresponds to E falling, then this minus 1 corresponds to D rising. Okay. So, this is correspond to D rising then you have A B falling. So, this corresponds to A B falling. So, this is basically whenever I am finding the critical path, I need to trace the slacks from the output or the primary output towards the primary input. The slack I need to see the which is having the highest negative slack to find the critical path. So, if whenever the slack is negative, then your circuit will fail in the actual design. We need to design or use another logic gate to satisfy that constraint, such that my overall required time should be satisfied. So, in this lecture we discussed about how to find the arrival time and required time and finally, the slack at each node of the circuit, which is useful for finding the critical path of any bigger circuits. It is if you have a negative slacks, then means that the circuit or the path is critical. We need to redesign the circuit to meet the required time given by the designer. Thank you for your attention.